Okay. So now that we have discussed the plant and station availability as well as the unavailability of various auxiliary systems, we will now discuss lesson 28, which is the effect of spares. So how many spares should exactly be available? Okay. Concept. Two most important concepts involved in a continuously operated and repairable system are the failure process and the restoration process. That we have been seeing the failure rate and the repair rate. Most of the techniques discussed so far have assumed that the restoration process associated with a permanently failed component is achieved. So how we achieve that? Either by repair of the failed component or by replacing the failed component with a spare. Okay. It is generally assumed that the spare is available. Okay. We have considered it is 100% availability when required. These assumptions may be invalid, and therefore availability of spares is an important criterion for reliability assessment. So whether the spare that you are talking about is available at the right time or not. Okay. In addition, it is frequently necessary to evaluate the number of spares that are required for a given application. Okay. A further application is in relation to the HVDC systems, which we are not going to see. It is not in your syllabus. Okay. So how to model the availability of spares? So what is the objective now? You have understood. The objective of this lesson is the availability of spares. Okay. So what is Markov model? We have already discussed. What is Markov model? The Markov model means state transition. That means we are saying that there is a state transition matrix, and with a fixed probability a system can transfer from one state to another. So this can be used to model and evaluate the probability of residing in, frequency of encountering, and duration in each individual and cumulated states. This is achieved by first constructing the relevant state space diagram. Again, we have to construct the state space diagram, inserting appropriate failure rate lambda, the repair rate mu, and installation rates gamma in this case, because we are considering a spare, and solving the resulting transition equations. As an example, consider a generating transformer substation, okay, that consists of two identical three-phase transformer banks. Okay, each bank consists of three identical three-phase single phase. This is not three-phase transformer. This is single phase. Okay, I have written wrongly. It is not three single phase or a three-phase bank, and is considered to have failed totally and must be removed from service if any one of the three single phase transformer in the bank fails, because that will result in three phase not being available. The bank can be returned to service when the failed transformer has been repaired or replaced. Okay, either repaired or replaced, and no further failures can occur in the bank once it has been de-energized and removed from service. Okay, we are considering only one failure, no other failures we are considering. So this is from the reliability book. Okay, I have taken this from the reliability book. So as you see here, this is one such state space diagram. Okay, so as you see here, the state 1 means both banks have no spare. Okay, now one bank down, state 3, that means you provide one spare, you install it with installation rate gamma, so that you have no spares and both banks up. Similarly here, one bank down, no spares. So in this case, the complete transformer is down, transformer system is down. Okay, like that you have got various states which you need to connect using the failure rate, the repair rate, and the installation rate of the spare gamma, so as to obtain this full state space diagram. Okay, now here there are, as you see, there are no spares. Okay, here in this case, in the first state there was no spares. Now here we have got one spare. Okay, so this is the typical state space diagram, which you can find out by analyze by considering each and every such states or possibilities. Okay, now we will try to understand by means of a numerical example. In the exam, only the theoretical aspects will be asked, so these examples are quite comprehensive. so it is not possible for you to complete them during the exam time. So it is only for aiding your understanding so that you understand the concepts behind it. Okay, no numericals will be asked regarding this. Okay, so consider a transformer substation which is to connect a 100 megawatt generator system to a transmission network. The following configurations are considered. Okay, so what you do, you take a single transformer bank with no spares, then one spare, two spare, three spare and four spares, and find out which should be the best, which has the best possibility. Okay, best reliability. Transformers of case 1 must be rated at least 100 megawatt. Okay, the range size between 50 megawatt when no redundancy is available and 100 megawatt total redundancy is considered in case of case 2. Okay, that means you have a 100 megawatt generator, but in case 2 you can either have a 50 megawatt spare or a 100 megawatt spare. But if you have a 100 megawatt spare, then you have a complete redundancy. Okay, redundancy means availability of additional unit. Okay, following data are used for each single phase transformer: 0.01, 0.1, 1.0 failures per year, repair rate 4, 12, 52 repairs per year, equivalent to repair times of 3 months, 1 month and 1 week respectively. Transformers take time to get repaired. Installation time, gamma installations per year, this is equivalent to one installation time about 2 days. So that means one transformer is out of a bank, it take at least 2 days to insert a spare. Okay, it takes lots of time to repair. Okay. So now we can, as I said, if you want to know the complete details of the results, you have to refer to the reliability book by the Willington book. However, we can have some indicating results. Okay, case 1. What was case 1? In case 1, we consider a single transformer bank with various spares, no spare, one spare, 0, 2 spares, like that. Okay, so in this case, the probability of the bank, so what actually is there in the result in this case? The probability of the bank be in the up state, the probability in the down state, and the expected megawatt depending on the level of the transformer. Okay, similar results can be obtained for case 2, which shows that state probabilities as a function of reliability indices and number of spares. So the state probability can be mentioned in terms of number of spares, and accordingly we will decide how many spares should be available. So detailed results can be obtained from the book. Okay, only for understanding, no need to, you can take up it as a project, but from exam point of view only the theoretical part will be asked. Okay, so again I will summarize. So starting with the plant and station availability, where we considered the boiler and the generator set, the generating set availability. Then we move to including transformers, where the transformer was either up or down. Then that was lesson 25 and 26, from which you are going to get numerical problems in the exam. And then in lesson 27 we discussed how the availability of auxiliary systems affect the output of a generating plant, and we saw that the generating plant is generally not completely out, rather it operates at some derated states. Now in lesson 28 we have understood the fact that the availability of the spares will dictate what is the output of a particular power plant, and we saw an indicative example of a 300 megawatt 100 megawatt generating station with a bank of transformers. Okay, so the only thing that is left out of this plant and station availability is the protection system availability, which we will see in lesson 29 tomorrow.